Hello, welcome to the tutorial on system level power analysis with IEEE 2416 power models at DVCon 2021. I am Nagu here, and along with my co-presenters, we would like to walk you through what the standard is about and how the standard can be used in different phases of the design flow. I'm Nagu Dhanwada. I lead a global team responsible for the development of power grid thermal and reliability tools across IBM. I also chair the SI2 UPM system level power modeling project. And I also founded, along with Jerry Frenkil, the IEEE 2416 standards committee, and I currently chair that committee. Now, in terms of the tutorial outline itself, I would like to start off with an introduction and overview of the standard, get into some level of detail of the standard, and try to highlight the use of the standard in the design flow, how it stacks up with the traditional flow versus the IEEE 2416 flow. And the rest of the tutorial, we have, we want to introduce different personas in order to highlight how the standard can actually be used in different parts of the design flow. And there'll be a deep dive into the use cases along with real world examples. And finally, we'll wrap things up. Now, in terms of the mission of why, of what the standard is about, the goal here was to develop a standard for system level power modeling that has very low barriers for adoption by the industry, right? And this was primarily motivated by the lack of a standard way to formally represent power data at the system level, represent IP block power data at the different levels of abstraction, and also represent power data for use at system level across a range of PVT points, all within a single model. Just to introduce of how we went about developing the standard, the goal here was to get to a realizable standard, right? The goal we started with was not just to create a spec and then hand it out as a standard, but more get a spec which has a good chance of adoption by having collateral to prove out the spec which goes along with the standard. Yeah. So what we did here was within SI2 spec was developed. The spec was contributed to the IEEE 2416 working group, and we iterate within the IEEE 2416 working group in refining the spec. And along with the refined spec, we go with the prototype implementation and proof of concept demos that go along with the standard. And here, in order to put together the prototype implementation and the proof of concept demos, we work very closely with our university partners in order to come up with all these before we release the standard to the industry. A quick, big picture timeline. We started back in 2014, and after a lot of, lot of contributions, discussions, challenges, we ended up, releasing a V1, formally a V1 of the standard at DAC in 2019. Process voltage and temperature independent modeling. And the third main aspect is model continuity and interoperability through formalism of data and interfaces, right? Both within design flows as well as across abstraction levels. So I'll get into details of some of these pieces, but that is really what the standard at its heart is trying to address. Yeah. Now, why do we need to address these, right? So first of all, really efficiency and accuracy are paramount for modeling energy and power impacts at the system level and beyond, right? So the whole notion of efficiency is delivered in terms of abstraction capabilities, right? In order to facilitate large-scale system simulations that are power aware, right? And at the same time, delivering accuracy in these models, which are used in these system-level simulations, are also very valuable so that we can avoid significant over-design and not have to build in large margins, right? So you clearly see that currently there is no standard way to represent power data across a range of PVT points. There is no standard way, again, to represent power data consistently across multiple design levels, as well as no standard way of providing power data to 1801 system level power models, right? The whole notion of PVT independent modeling significantly helps in the efficiency part of it, which I mentioned, right? It reduces the effort for multi-corner characterization. It does not it kind of precludes the need for inaccurate interpolation and extrapolation, and the whole notion of design continuity, right? I mean, and across design levels, across abstraction levels, is also needed, and it's actually facilitated through some of the contributor-based modeling concepts, which we'll introduce later in the presentation. Right. So now to get into the how part of it, right? Before we get into a little bit more details on the how part of it, we would like to address some of the needs. To really introduce the notion of what we call as the power contributors, right? So this forms basis for the PVT independent modeling aspects of the UPM standard, right? So if you really think about it, contributors to power dissipation are mostly separate, right? They can be separated very clearly, and they encapsulate different device physics, right? So examples of these are, let's say, the channel or gate leaking width of devices, the switching of a capacitance, and the crossover current, for example. These are all, you can actually separate the power dissipation into components like these, right? And that's the inherent ability of how to model power, right? So these separable components of power are called power contributors, right? So the total power is a sum of these separable components, and basically each contributor behaves the same in different cells, thus giving us the ability to share contributors amongst multiple cells, right? So this concept of contributors, which we'll elaborate a little bit more on, have been proven and successfully used on several generations of microprocessor designs within IBM. Yeah. Now, the little bit onto the how part of it, right? So think of power contributors as nothing but power proxies, right? So in a traditional power model, we have power data is actually stored in the model, right? But here, the power data is not stored in the model. Instead, the contributors to power are stored in the model, right? So think of structural aspects of the design being stored rather than evaluating the power and storing the power in the design, right? So examples of these power proxies are a leakage power proxy, which is essentially, let's say, leaking transistor width, right? And that is the one part which is actually stored in the model itself. And from that, leakage can be calculated using the W effective, the effective leak transistor width, which is stored in the model, and using certain parameters provided by the user at the time of evaluation. And similarly, you can also think of an energy proxy, which models your dynamic power, where you essentially store equivalent capacitance in the model and not the dynamic power in the model. So essentially, you're storing the equivalent capacitance, and for you to get to energy and dynamic power, you will use the C effective, which is stored in the model, and then provide the voltage, temperature, and state, which could be provided by the user at the time of evaluation. Yeah. So now a little bit on how this kind of the contributors and hence PVT late binding improves power flows. If you think about it, in a conventional library power flow, characterization is done for every cell at every PVT point of interest, right? So that is, the PVT conditions are applied during power model generation itself, right? Which leads to us requiring a large number of circuit simulations. And the fact that the power analysis is specific to a particular PVT, it has the early binding. Now contrast that to a contributor library-based power flow where there is a single PVT independent power model is generated from the power model build step that works across all corners, resulting in minimal library characterization effort with no simulation needed. And the right. So the generation step itself in a contributor based flow is essentially some sort of structural analysis of the library and the design to come up with the PVT independent model. And when you are actually calculating power, you apply the PVT points, which kind of leads you to this lazy evaluation / late binding kind of a concept, right? Which makes it very easy for you to literally do analysis at any PVT point. Right? So even though the 1801 standard added power state modeling capabilities in the terms of the power expressions, intentionally, the data representation for power was not addressed in that standard, right? So what 2416 accomplishes when interfacing with 1801, you could think of it that 2416 formalizes the semantics for power abstraction of complex IP and models PVT independence, and it kind of formalizes how the data is stored. And the 1801 model literally captures the power states and power domains. It captures logic expressions determined during the current power state. It affects the parameters. So it captures the whole logic and transitions and everything. And the power expression data or the power data is formalized by the 2416 standard. Right. So the UPM standard itself, right, is set up to be a multi-level model that can serve up power data throughout the entire SOC flow, right from 1801 system level power estimation all the way to gate level power estimation, right? So in this multi-level structure, at the highest level are applications that use the 1801 models, right? The system level portion of a multi-level UPE model will serve up static power and dynamic power numbers through the system level data and the associated power expressions, right? And at the lowest level of this multi-level structure would be the contributor level, where the data is stored as contributors, and the contributor evaluator converts this data to static power per state and energy per event to be provided to Liberty applications, right? Now, in addition to serving up data to the Liberty applications, there could also be new EDA applications that could directly consume the contributor level data, right? Now, in the middle is the gate level or direct level of the multi-level model, where we could have Liberty-like data that is served up via power expressions to the 1801, or directly the static power per state and energy per event can be served up for Liberty applications. We use a XML schema. So this is, think of it like a self-checking model where the model structure is described in an XSD schema, and there's a formalization of the model contents, and the schema enables automatic model structure validation itself. Right. Now, getting on to the overall model architecture itself, right? You saw the, in the slide, we show the 2416 library on one side and the power tool, which is actually using the 2416 library. The general architecture, again, as I mentioned a little bit earlier, is a multi-level architecture, which provides backward compatibility with existing gate-level models. Right? This architecture also enables a single model with multiple levels and multiple representations to be used at various phases in the design flow. Right? The gate level provides the storage of data for backward compatibility with legacy modeling approaches, right? And the power and energy data returned from this level are identical to that provided by Liberty, essentially, right? So these are the static power per mode and energy per event information, right? The system level again provides for interoperability with the 1801 component power state models, and the output from level is consistent with the 1801 power expression attribute of the add power state command, which expects to receive static power and dynamic power for a defined state. Right? Several inputs need to be added to provide this power data, including the operating frequency and others, depending on how this 1801 model is configured. If we need a voltage independent system level power model, the data may be represented directly by expressions, right? And of course, at the lowest level are contributors, which can go through a contributor evaluator, and that can also feed back into legacy Liberty-like applications as well, as I had mentioned a few slides back. Yeah. Now, a little bit on the contributor evaluator. The contributor evaluator is an expression or a set of expressions that evaluate a contributor using specified parameter values in order to return power or energy. Right? The UPM specification does not mandate any particular implementation, and it can be anything from a simulator to a simplified set of equations that are evaluated in line to compute the power and energy values. Right? So here you see, the input are the contributors, and there are also a process parameters as well as environmental conditions, which are input to the contributor evaluator, and the output you see energy per event and leakage power per state. Yeah. Can you see here there are a bunch of cell parameters which come from the workload, and there are some expression parameters which come from characterization, and then the dynamic power itself is actually shown in the model here. I just want to quickly highlight the use of it in a generic system to silicon power aware design flow. Right. So in essence, you can think of the flow, a generic design flow to consist of three phases. Right. One is our electronic system level. There's an RTL design stage, and there's an implementation stage. Right. Each phase, to varying degrees, contains a design, analysis, optimization, verification tasks, and each phase relies upon the availability of accurate and efficient models, and each phase produces power data that is passed down or forward to subsequent phases. Right. In order to realize this flow, multiple power-aware technologies are required. You need various tools, like simulators, synthesizers, etc., languages, formats, and models also. Right. Here we see some representative power-aware activities on the right-hand side of tasks that are relevant and typically undertaken during each design stage. Right. And for these activities to be effective, power data and power sensitivities to the various modes, stimulus, etc., are really required. Right. So clearly, in the overall flow as it stands, there is a lack of high-level power modeling capabilities, lack of standards for high-level modeling, and there are lack of models that can actually work easily across this ESL, RTL, and implementation stages. Right. So for us to really deploy a comprehensive power flow, right, which encompasses ESL, the whole system level, through implementation, we need models for each design stage. Right. So today, while very, we have very good modeling capabilities, which exist at the lower levels, at the higher level, there really are no standards, right? And execution of this ideal power-aware design flow is limited by model availability, right? Now, here is where UPM comes in order to, bridge this gap through an efficient multi-level model architecture and provide several efficiencies like contributor models while ensuring backward compatibility. So different personas who would be involved with the different aspects of the flows. So now, if you think about who will benefit from the standard, there are, we can think of three categories. There are model creators, model consumers, and tool providers. An example of model creators are IP developers. And we have Professor Rhett Davis, who is going to present how the standard will benefit from the point of view of an IP developer as well as the tool provider's perspective, while the model consumer aspect of it, in terms of system architecture and how a system architect can derive value from the standard, is going to be presented by Jerry Frenkil. And the SoC designer who is going to use the IP and actually build the system on a chip, the perspective from an SoC designer is going to be presented by David Ratchkov. So with that, I'll hand it over to Professor Rhett Davis.
Hello, I'm Rhett Davis. And I'm going to describe IEEE 2416 from the perspective of the IP provider. I'll do that by taking on her persona. So call me Izzy, the IP provider, for the next 9 slides. In reality, I'm a professor at NC State, and I also serve as technical and education advisor to SI2. I've also been a member of the IEEE 2416 working group since it was created. Now, as an IP provider, my main goal is to provide a verified library of cores with a balance of power, performance, and area that my customers want. My customers, who are building systems, need power models, and they want me to provide them, or enough detail so that they can create them themselves. Though in general, I'd rather provide the model to protect my IP and avoid sharing those details. So in the next 7 slides, we'll see how I can provide that model using IEEE 2416. At the same time, to diversify my risk, I want to target my core for as many foundries and EDA providers as possible. Doing so increases my customer base, but it creates a problem for me, namely that I could potentially multiply my effort having to tune my core or regenerate my libraries for every new process and tool. Hopefully, as the IEEE 2416 standard matures, more EDA providers will support it, which eliminates one of those problems. And in a few slides, I'll show you how 2416 minimizes the effort of retargeting a core for another foundry. First, let me illustrate the core that I'm providing. Let's say that I'm providing a CPU core like the Rocket Tile from UC Berkeley and the Free Chips Foundation. It includes standard cell libraries, standard cells and memories. It has a processor CPU. It has caches and bus interfaces. So this is what I am providing a power model for. So where do I start if I want to know how much power this core uses? So this slide shows a typical state-of-the-art power characterization flow. I create benchmarks for targeted power scenarios. I run Verilog simulation to generate switching activity. I feed this activity into a power estimation tool or flow, along with standard cell libraries and memory libraries. These give me report files, which I can parse with custom scripts into spreadsheets, which are my normal way for collecting power data. Now, there are a number of problems with this flow. First and foremost, it can take hours to run and takes gigabytes of storage. And I have to repeat this process for every single PVT point that my customers want. And that's a lot of expense. Second, once I have generated the data, I have to ensure the consistency and traceability of every point so that we can debug mispredictions. That's also a lot of expense. And third, what do I do if I'm missing the libraries for the desired PVT point or process? How can I proceed? Well, first of all, 2416 helps me to manage my data. Using XML table elements, I can track all of the details for the static and dynamic power for each benchmark, which appear as power states, just like they do in the 1801 standard for power intent. Here I'm showing a 2-dimensional table with indices of voltage and temperature, but the standard supports as many indices as I want in as many dimensions. And I've listed here the kind of indices that we typically use for static and dynamic power tables. Now, in the working group, we call these top-down models because they are built from power samples taken with a top-level view of the design hierarchy. And they more or less represent the typical way that we manage power data today. So great. 2416 helps me to manage my data more easily than before. But what if I can't generate the data because I don't have the libraries, or because I want to target a new process? Well, in order to predict power in those cases, I need to take what I know about the structure of my core and extrapolate the power for new PVT points and processes. This is what you'll hear us call a bottom-up model, or a PVT independent model in the 2416 working group. To be the most useful, I would like to replace my top-down model with this bottom-up model, which means that I want it to be equally accurate. I can accomplish this by capturing the structure with contributors, which come in two flavors: static power and dynamic energy contributors. Now, Nagu introduced these contributors earlier, but let me show a bit more detail, starting with the static power contributor. Now, leakage current varies quite a lot over the range of process voltage and temperature, but it can be predicted with node voltages, which don't vary that much. So if I want to accurately predict the power for a complex design, I have to decompose it into cells and decompose those cells into a set of transistor stacks or contributors, and then pick a transistor in that stack, and then characterize expressions for that transistor's node voltages. Once I have those expressions, I can predict the current for any PVT point very quickly by using the same SPICE models that were used to characterize the cell. This new model has nearly the same accuracy as SPICE, but it is much, much faster, mainly because there are no Newton-Raphson iterations, and also because the number of different contributors just isn't that large. So for the sake of time, I will have to leave the discussion there, but I've given you a reference to one of our ISQED papers that describes this process in more detail. So now let's discuss dynamic energy contributors. Unlike static power, dynamic power varies much more with activity than it does with process and temperature, but it can be accurately predicted with events, using this expression here. So if I want to accurately predict the power, the dynamic power for my CPU, I need to decompose the power into a set of events, and then characterize the amount of switched capacitance for each one of those events, represented by Cj in this expression. Then to estimate the power, I just need to count the number of events Nj, little n sub j, over a number of cycles, capital N. And then I can predict the dynamic power using this expression. So for the example that Jerry will show you later, we characterize the contributors for each RISC-V instruction running on the rocket tile, as shown in this bar chart. As you can see, over the range of instructions, the power varied by a factor of about 2.5, which is typical. So I'd like to thank Alan Baker, formerly at ANSYS, who did all this power characterization for us using their tool, Power Artist. And I'd also like to thank the creator of the tool Microprobe from IBM, which is what we used to generate the workloads for this flow. So now this instruction level power model is really just the beginning. We can keep adding events as needed in order to increase the accuracy. And if we had more time, I would show you how we incorporated cache fill events into this model as well. It's also important to note here that 2416 doesn't tell me how to decompose my core into these contributors, either dynamic energy or static power. but it does enable me to automate the entire process of characterization and estimation. So once I'm done, I have a complete power model that allows me to perform system-level power analysis over as wide a range of process voltage and temperature with as many dynamic voltage and frequency scaling scenarios as I or my customers want. It's much faster and requires much less storage than the flow I showed earlier. And because it uses a simplified flow shown here to simply count the number of events and then estimate power using this 2416 power analysis tool. And it's relatively easy to extrapolate to a new process. So let me leave you with this image from the example that you will see soon that illustrates the simple flow, predicting power over time as we change these PVT and DVFS scenarios. So now let's pause, and I'll take off my Izzy hat and put on the hat of Eddie, the EDA provider, and take the next 5 slides to talk about 2416 from the EDA provider's perspective. Now, as an EDA provider, my goal is to provide tools that enable successful state-of-the-art designs in current and future technologies to as many users as possible. My customers want full system power modeling capability, and they want me to develop it for them. But they don't want to share their data, which makes it difficult for me to show how my tool solves their problem. Now, 2416 helps with this problem by being a medium for sharing that critical data needed to develop this capability. Also, as I develop this new capability, I want to ensure that my tools satisfy a number of other criteria. I want them to be fast, efficient, and accurate. I want them to use the same or similar power models across all levels of abstraction so that I don't have to support so many formats. And I want to be sure that they're going to stick around for a long time. And I want to make sure that they solve my customers' problems so that they can be motivated to keep buying licenses. Well, as I said earlier, 2416 models can be very fast, efficient, and accurate. They can be used at the system level all the way down to the level of the standard cell or the contributor. And the IEEE standard helps to ensure that they'll be around for a long time. So it hopefully satisfies the first 3 of these criteria. But how do I know that it's going to solve my customers' needs? So let me show you 3 potential applications that we think could be enabled with IEEE 2416, which serve as examples of the tools that we think will be in high demand. The first application is simply to provide fast system-level power calculators. All system architects want this capability. And as evidence of this claim, I will point you to the fact that the vast majority of them use the free tool MacPat, despite its well-documented incorrectness. I've included some images below from one of my favorite papers from Andreas Gerstlauer's group at UT Austin, where they are using machine learning with power samples taken from real hardware to tune MacPat models to be more correct. Now, rather than tune MacPat, I think it would be much simpler and more useful to use machine learning to extract a more correct 2416 model for a CPU and then deliver that. There's every reason to believe that these models would be in demand just as much as MacPat is now. The second application is pathfinding, which is the term for physically aware virtual prototyping for the purpose of technology selection. This is especially useful for a 3D IC chip stack design. And I've included a reference to a paper, one of our papers, in which we used transaction level power models to explore different floor planning options in a 3D IC. The first two plots here are showing how much faster a thermal runaway was reached when we floor planned these cores on top of each other rather than distributed. We also explored the impact of throttling the processor before it reached thermal runaway, as shown in this third plot. So this was all done with homegrown tools that were not particularly reliable. But with a combination of 2416 and the 1801 standards, we can actually start to build reliable floor plan optimization tools that take things like chip stacking and DVFS into account. So building on this idea of combining floor planning with thermal solvers, the last application that I will mention is temperature reliability co-optimization, which is the idea that you can trade off performance and lifetime of a multi-core system with creative scheduling of workloads. This is because the different mechanisms for transistor degradation become dominant at different temperatures. I've included images from one of my favorite papers on this topic that appeared 7 years ago. Again, we see that this work used MACPAT despite its inaccuracy, but it's reasonable to think that if an accurate alternative were available with 2416 and 1801, the designers would want to start using it. So that was my last new 2416 enabled application, but I suspect that there are many others just waiting to be developed. So in summary, the 2416 standard enables full system power modeling capability in a way that is fast, efficient, and accurate. It gives me continuity in my power models all the way from the system level down to the standard cell and contributor. It gives me a way to interact with my customers, and it enables a wide range of long expected tools. So that concludes my talk. Thanks for listening. And now I will hand the presentation over to Jerry Frenkil, who will talk about 2416 from the system architect's perspective.
Thanks, Rhett, and hello, everybody. I'm Jerry Frenkil from SI2, and today I'll be speaking as a system architect and describing how IEEE 2416, also known as UPM, helps me to do my job. I'm currently a technical advisor at SI2, where we developed UPM. I'm also vice chair of the IEEE 2416 working group, where we formally standardized UPM as IEEE 2416. As a system architect, I have several goals regarding throughput and performance, cost, schedules, power, and reliability. And I have specific targets for power consumption and junction temperature too. I'm concerned with managing my risk as I pursue those goals. To do that, I need to have early estimates for energy, power, and temperature to guide me in my design decisions. It could be a career-limiting move if I don't find out where I am relative to my goals until late in my project. I need early, accurate information. In pursuing my goals, I will design with IP from multiple sources, various external IP vendors, as well as internal IP design groups. Each of these different groups is likely to provide their data in different formats, scalars, tables, graphs, or expressions. That is, if they have it. Many don't. Delivery mechanisms vary too, from data sheets to spreadsheets to proprietary formats or gate-level netlists that I need to simulate myself. Finally, sometimes, when my IP provider can't or won't provide the data I need, then I need to build my own models. As a systems guy, I don't want to build models, but I will if I have to. So to achieve my goals, I have several wants and needs. Chief among these are early, reliable system-level power estimates and thermal estimates. I want to see, at the block level, power consumption values and junction temperatures. I need to know that the total energy consumed at my worst-case temperature, but I likely won't know a priori what that worst-case temperature will be. I would like my models to support successive refinement flow. By successive refinement, I mean that I'm willing to work with estimated or first-order models early in my design project. But I want mechanisms by which I can easily refine or replace my model with more detailed data when it becomes available. This is especially the case with regards to temperature. I also want an efficient mechanism for rolling up power estimates for my entire system, all components, all functions, analog and digital. And I do not want to use a spreadsheet. They're too error-prone and require too much effort to create and support. So this is the roll-up I don't want. Nevertheless, this is generally how full system results are collected today or rolled up today. But this is a big challenge, setting up, debugging, and maintaining this full system roll-up for multiple scenarios, a full system of 20 or more devices, static and dynamic power, analog and digital blocks, 3+ scenarios, actually many different scenarios. So as an architect, I need a more effective power roll-up than this. I need accurate, reliable results without requiring too much modeling effort. Spreadsheets can be accurate, but are often unreliable, and they require way too much effort to support. I need something better. Fortunately, there is a better way with IEEE 2416, which was designed to meet my goals as a system architect. Here are some of the key features. Multiple data representations are available. Scalars, multidimensional tables, expressions, and a new construct, contributors, which are PVT independent power proxies. And whatever the representation, static and dynamic power are represented separately. This PVT independence means for me that I only need a single model to represent whatever corners I need to analyze. And importantly, UPM was designed from the ground up to be interoperable. It's designed to interoperate with other languages and standards, such as IEEE 1801 or UPF. 2416 is built on standard languages, XML and Verilog A. And 2416 is itself now an industry standard, being formally approved by the IEEE. These features enable me to discard my spreadsheets, automate my use case scenarios and evaluations, and do much more. 2416 supports a couple of different power analysis flows as shown here. On the left is a post-simulation time flow, and on the right is a simulation runtime flow. The flow on the left, the post-simulation time flow, is generally well known and well used for gate-level power analysis. Basically, the design is simulated and a VCD trace is captured for all the signal transitions. 2416 models can be used in the same manner, with the big difference being that all bit-level signal transitions are neither needed nor captured. Instead, event counts are captured for specific model parameters, and power is calculated based upon the 2416 model and the captured event counts. The flow on the right, a simulation runtime flow, does not require a separate power tool, but instead requires a UPF 3.0 or 1801-2015 compatible simulator and communicates with 2416 through the 1801-2416 API. So here is a snippet of a RISC-V processor model modeled in 2416. This model is an energy per instruction type model, which is simple and elegant. In an application, we count the number of times an instruction is executed. Here we show the load and store instruction definitions. And then multiply that number by the characterized energy for each of the instructions. The rich set of 2416 semantics enables this straightforward representation of the processor power characteristics. Note that this is a voltage and frequency independent model. This means that this model can be used to evaluate power consumption at any voltage and any frequency. This is but one example of a 2416 model. Next, let's look at how this model could be used to evaluate several use case scenarios. The design shown here will be used to illustrate the power analysis of a dual-core RISC-V SoC. Each of the rocket tiles will be modeled with a single top-down energy per instruction model. The model is parameterized by the counts of each executed instruction. The other three blocks, the system bus, the memory bus, and the TL to AXI interface, are each themselves modeled with an individual top-down model. Shown here are 10 different analysis scenarios for this design. Basically, a thermally aware DVFS system in which the operating voltage, frequency, and junction temperatures vary with each time slice. 4 different workloads are used in this analysis, which computes power for each of the 10 unique scenarios. We'll vary the frequency from 100 megahertz to 1 gigahertz, the supply voltage from 9/10 of a volt to 1.1 volts, and junction temperatures from 35 to 110 degrees C. To illustrate the efficiencies of using 2416, think about how you might do this with a spreadsheet. Shown here are the automatically generated roll-up results of the 10 different use cases shown on the previous slide. 2416 for this analysis was used to model all system components, and a single 2416 voltage and frequency independent model was used for each of the scenarios. So we see here that 2416 enabled a fully automatic analysis and roll-up of the entire system, thereby enabling me to avoid spreadsheet-based roll-ups. Now, to summarize a system architect's view of what 2416 means. 2416 can model all parts of the system with its rich modeling semantics and data representations. 2416 can be used in successive refinement flow with simple models early on and more detailed models as more details become available. 2416 robustly replaces spreadsheet-based system roll-ups, as we saw with the DVFS example. And finally, as a system architect, 2416 makes my life easier. And I like that. Next up, David Ratchkov from Thrace Systems will talk about 2416 from the perspective of an SoC designer.
Hello, everyone. I will discuss IEEE 2416 models from the point of view of SoC designing. My name is David Ratchkov. I'm the founder and CEO of Thrace Systems, provider of system-level power analysis tools. Our Power Meter platform is the first tool to generate and utilize 24 system models for system power analysis. And I'm very happy to talk to you about the benefits we see from 2416. How do we go about generating them, and how do we go about using those models? I'm also co-chair of CDX workstream under the OCP's Open Domain Specific Architecture. And together with Jawad, we are working on formalizing data exchange needs and formats for early chiplet architecture analysis and design. As a designer of an SoC, I need to generate power analysis. And while doing this, I will encounter several obstacles. For early designs, I'll have difficulty collecting complete models for all IPs in my SoC. Some may have measured data, some may have just spreadsheet estimates, some may have data only for older technologies. Yet for some of the IPs, I may have a power model, but not at the right corner. And most certainly, libraries will not have power models for all my PVT corners I need, and I will need to fudge my results to generate the PVT data I need. If I'm early in the technology cycles, I will have models from my IPs from previous technologies, which is actually exactly what happened to us while we were working on this tutorial. We had libraries for the standard cells, but not for the memories for our target technology. We only had the memory models from the previous technology. I will show you later in the slides how I solved this problem by mapping the models to our target technology. And last but not least, when I'm done with all analysis as an SoC designer, I need to provide this information for integration into the bigger system. And I would like to do this in a tool-readable format. 2416 solves all these needs. First, it enables me to estimate power at any PVT point I need with a single model. And it solves this by capturing enough proxy information for the circuit and lets me perform late binding to a process model, at which point I can specify my PVT points. Professor Davis explained this in his slides, and later in my slides, I have an example of a model as generated by Power Meter. I also have an example of how 2416 enables technology mapping. I can then perform power analysis using a complete set of models. I can capture my power analysis results in a 2416 model and hand that off to the next level of analysis, such as architects, system and product engineers. Overall, 2416 allows me to receive and deliver data in a common, standard, tool-readable format. A bottom-up 2416 model with power contributors is what enables me to perform power analysis at any PVT point I like, using a single model. How does that compare to the classical models which are available today? In the case of a classical model, the circuit, including the process model, is treated as a black box, and the simulation captures current on the circuit boundary. This creates a simple model, but with the drawback that the model is PVT specific and all information about the model and the circuit is actually lost. If I wanted to get data at different PVT or using a different process model, I will have to generate that model from scratch, and I will need to have a model for every PVT point. 2416 does this very differently. 2416 captures enough information about the circuit. It captures its topology and just basic information. Binding to the actual process model and the specification of PVT is done at a later point, at the point where I want to estimate power. This is how I can actually estimate power at any PVT point and with any process I like, any process model I like. The resulting 2416 model is surprisingly not more complicated than classical power model, nor it is any slower to analyze. As you can see in this comparison from our tool, the data set of a Liberty library at 5 corners is already much larger than the corresponding 2416 single power contributor model. And again, with this single 2416 model, I can cover any corner I like, not only the 5 corners which were available from the Liberty. Additionally, for a library that's very limited set of power contributors, and that is because power contributors are shared between different circuits. Because devices may reside in similar topology and thus contribute the same amount of leakage. As would be an example of a buffer with just different drive strengths, where similar transistors in similar states are going to contribute the same amount of leakage, and we can combine this down into a single power contributor. This makes the resulting 2416 library smaller, more compact across PVTs, and definitely not any slower to use to work with. Very often, as an SoC designer, I'm asked to estimate power for a new technology for which I do not yet have data. However, I have a model from earlier technology. Before 2416, I may do this by using fudge factors and hope that those were good, not too optimistic and not too pessimistic. We actually had the same problem with our tutorial, which we had to solve. we did not have models for our SRAMs for the target technology we had. We solved 2416 solved this problem as well. With Power Meter, I generated 2416 model for the other technology and used mapping to generate model for our target technology. The result was a new 2416 model for the SRAM for my target technology. And I know that this model is going to be very, very accurate and definitely way more accurate than any fetch factors that I may have used before. Generating bottom-up 2416 models has several applications in several cases. In the first case are hard IPs, such as memories and standard cells. These are IPs for which I expect to have at least a SPICE netlist for simulation and a single library file, Liberty library file for timing analysis. The SPICE netlist and the Liberty files enable tools like Power Meter to generate 2416 models in a simple way without any other user inputs. This makes generating 2416 model trivial and very fast. The other case where I need to generate bottom-up 2016 models is for an IP for which I do not have a design in my target technology. As I previously mentioned, this is where I would use technology mapping. I have the design from the previous technology. I have generated the model for that. And I need to map to my target technology. The only additional information that's required in this case to generate the target 2416 model is the device mapping between the two process technologies. In our case, we got the device mapping from Professor Davis, who provided us with the data, and we're able to map the SRAMs in our test case from the original technology down to our target technology by using this device mapping. The third case where I need to generate 2416 model is when my design, which is either a block or a complete SoC or even a chiplet system, includes components for which I have 2416 models generated by one of the methods I have described earlier in the slides. In this case, inputs to the tool are only design data, such as netlist, capacitances, and 2416 models for all the components which are in my design. Just with this information, I can generate 2416 model for my design, which can be a block SoC or chiplet system. If I wanted to estimate power, I will need at this point to use a process model. Interestingly, using 2416 models is as simple and looks exactly the same as generating the 2416 model. In fact, it is the same flow, and this is on purpose. Remember, as an SoC designer, I need to both make sure my design meets the power targets I have been given, as well as being able to provide power data to downstream users. I accomplish both using the same flow and using the same model. As an SoC designer, 2416 models meet all my needs for power. I can receive power models from IP owners and deliver power models to other SoC designers and architects. As a user of these models, I can estimate power at any POT without the need to regenerate the model itself. Most importantly, with the late binding of process model, I can quickly generate new estimates for process models, for process model updates, without the need to regenerate the model, or altogether map 2416 model to a new technology. And most importantly, I'm using a single model, not only to estimate power at different POTs, but also estimate power at different usage scenarios. Thank you.
Thank you, David. I would like to wrap up this tutorial by first highlighting the impact and value of power-aware design flows, which are centered around the IEEE 2416 standard will be, right? So first, there are cost savings which can come through the adoption of the standard, basically coming through pessimism removal. There could be schedule and compute resource savings, which can also come into play here, mainly because you have detailed insight into sources of power consumption, and from the whole multi-corner power analysis runtime savings, and significant productivity improvement by having a multi-level model encompassing your end-to-end environment. And clearly, the efficiency and accuracy will help in creating power-efficient designs. Now, to wrap things up, the IEEE 2416 standard takes a significant step towards formalizing power data across multiple levels of abstraction. We released the first version of the standard in May 2019. We also shared some tools and demos that highlight that this standard is something which is realizable. And more specifically in this tutorial, we shared the RISC-V modeling. Now, there are early versions of the tools, both from SI2 and Thrace systems, which are available to generate and consume the IEEE 2416 models. Please join us in the IEEE 2416 working group. We have work on the next version of the standard starting soon. For more information, there are web resources, and you can contact any of the authors using the email listed here. Thank you all for your attention, and appreciate you spending this time with us in trying to learn more about the 2416 standard. Have a great day. Bye.